Welcome back, guys. This is our lecture on Newton's third law of motion. Let's get started. This is Unit 2. So again, where does this come from? Chapter 6 of our textbook. If you have a hard time with the explanations, always look there. Reading assignments are also aligned with the textbook to help you out. All right, as a quick recap, we have many different types of forces. We said previously that we have two types of friction. We have static friction. This is the force of friction between two solid objects that are not moving relative to each other. So this is stationary friction. And this is the friction that has a greater maximum value. Once you get an object to start moving, then you have kinetic friction. Kinetic friction is the friction that acts between two moving surfaces. This one tends to be a smaller force of friction. It's not as great of a push, smaller force. Then we have weight. That's the force of gravity on an object. Often confused with mass, but weight is an expression of mass as a result of gravity. Mass is the most basic, or the more basic of the two. Then we have normal force. That's a contact force that is perpendicular to two surfaces in contact. It keeps two surfaces from penetrating each other. It often opposes gravity, and what we mean by that is if you have a box, say, on a table, like right here, weight is pulling it down, that's the force of gravity, and then the normal force is the table pushing up on the box to keep it from penetrating the table. We have tension. Tension's a pulling force on an object, just like pulling on a rope from both sides. Compression is a squeezing force on an object. If you were to take, say, a giant spring and squish it, we'd say that's compression. And applied force is just a standard push or pull by any sort of object. All right, and so Newton's given us his second law so far. Acceleration is caused by force and limited by mass. But he has a total of 3 laws, and his third law came as a result of an observation. We said that force is a push or a pull, but Newton's observation is really that force is not a thing by itself, but it's part of a mutual action between two objects in interaction. So a force is itself, ultimately, what is a push or pull? It's an interaction, okay? And so that means that you don't have a force occurring by itself. It really occurs in sets of twos. Here's an example. If I go ahead and try to hammer a nail into the wall, well, when I actually hit the nail, there's going to be the force of the hammer on the nail itself. That's our objective. But the nail itself is going to resist motion, and there will be a pushback on the hammer from the nail. So the nail will get hit, and the hammer is going to get pushed back with the same force on it that it hits the nail with. Okay? So every force occurs does not occur by itself. It occurs in pairs in an interaction. Forces come in pairs. All right, here's a quick thing to try. Can you touch your desk without your desk touching you? So go ahead and try and touch your desk without your desk touching you. You can't do it, right? If you try to touch your desk at all, well, as soon as you touch the desk is touching you. It's pushing back up on you. So all forces occur in pairs. That was Newton's observation that led to his third law. So what does his third law actually state? It says whenever one object exerts a force on another object, the second object exerts an equal and opposite force on the first object. We call the first force the action force, and the second force, the response, the reaction force. Okay, here's another example. If we are this wonderful smiling person here, and we lean against the wall, right? We're pushing on the wall, and the wall is pushing back on us, right? We've talked about an example of this so far with the normal force. Why don't we sink into a table or a chair if we're sitting on a chair? Because the chair pushes back up on us. Right? The normal force is a reactionary force. So Newton's third law says for every action, there's an equal and opposite reaction. If we push on the wall will push back on us. All right. What if we wanted to go about identifying action and reaction forces? Well, there's a method to doing this. The simplest way is to write out the objects involved. So you'd write action, object A pushes on object B. Reaction is object B pushes on object A. And you're like, well, Mr. Mellor, why would we, bother with that? Well, we have very different results when our forces act on different objects, right? Because even if they say, if I have a person standing on a scale, right? He's pushing down on the scale's pushing back up on him. We have a man standing on a bridge. He's pushing down on the bridge with his weight, and the bridge is pushing back up on him, right? The action force acts on one object, right? Object B. The reaction force acts on a second object. And with two different objects, we have two different masses, and with the same magnitude of force, we get two different accelerations, and then you get motion between two objects. All right, let's practice a little bit. Here's an example. A fist hits a wall. That's our action. Our reaction is that the wall hits the fist. Okay, so object A is the fist, object B is the wall. Object B in our reaction hits the fist, object A. Okay, our action in this one is our head bumps the ball, A. Object B. What should our reaction be? Go ahead and try that on your own. Okay, well, it must be object B bumps object A. That's our reaction. So ball bumps head. Not too bad. Here we have windshield hits bug. Object A is windshield. Bug is object B. This is our action. Our reaction is what? Go ahead and try that on your own. Bug hits windshield. Okay, and so with all of these action-reaction pairs, the same force, the same magnitude of the force is applied to both objects, right? When I'm standing on the ground, I'm pushing on the ground with my weight, and the ground is pushing up on me equal to my weight, so I don't start sinking into the ground. But what if we have different masses? That's kind of the key question. Here's an example. If I have a handgun and I shoot the handgun, well, there's a force of the gun on the bullet that causes the bullet to accelerate from Newton's second law. That says that Newton's second law is acceleration is caused by the force limited by the mass. And at the same time, because all forces occur in pairs, this is Newton's third law, all forces occur in pairs. If there was a force of the gun on the bullet, there must have been a force of the bullet on the gun, the bullet pushing back on the gun. And yet, for the bullet zooms off, and the gun barely moves at all. So why? Because they have the same force on them, the same size of the force. Newton's third law tells us that. The answer is the gun has a much bigger mass than the bullet, right? Newton's third law says if they both have a force of 10 newtons, then the one with a larger mass, we'll say 100 newtons, that's 0.1 meters per second squared for our gun. For the bullet, right, maybe we have 1 kilogram mass. That's 10 meters per second squared. So why do we see the bullet zoom off and the gun doesn't recoil very much, doesn't move very much? Because mass is what makes the big difference. If we talk about our friend the whale being pulled towards the Earth, well, he's experiencing the force of gravity from the Earth. The Earth is actually being pulled with the same force of gravity upwards. Why does the Earth not accelerate very much? Because it has a huge mass for that tiny force of gravity from the whale. Whereas the whale has a very tiny mass in comparison to the mass of the Earth. And so they both experience the same force from Newton's third law, but the masses give us very different accelerations. Okay, one last concept. Why don't action and reaction forces cancel? We said that we get different results as a result of having different masses. It depends on how you're looking at your problem. If I have Mr. Mellor versus Dwayne "The Rock" Johnson in a tug of war game, right? I'm pulling this way. Dwayne "The Rock" Johnson's pulling that way. Why do we have motion at all? Well, if I consider just Mr. Mellor, if I'm thinking about what happens only to Mr. Mellor in this scenario, yeah, I am going to be pulled to the right. They don't cancel out. These forces are pointing in opposite directions. They don't cancel out because I'm just considering what happens to Mr. Mellor. If I consider what happens to a system that includes Mr. Mellor and the Rock, well, those forces are now internal to the system, and they would cancel out. So physics is wonderful because we get to choose what we're looking at. If I want to find out about the motion of just Mr. Mellor, then we would see the force pair would make a difference. If I'm looking at the system of both Mr. Mellor and the Rock, the forces would cancel. Here's another way of thinking about it. Inside of your body, your heart is constantly pumping. That's a force, right? So why doesn't that individual force affect your overall motion? Because it's inside of your human body system, okay? So internal forces cancel. External forces don't cancel. All right, that's it for now. We'll do some clarification and practice on this over the next couple of days. All right, see you guys.